You all are. I'm ready and we can get started. So I love that our adult told us that there's so many of us today that using that chat feature will be an excellent option for us. So my name is Miss Audrey and I am here at the Children's Science Center. And I have a special friend with me who's behind the camera and her name is Miss Maya. You might hear her voice, but you may not see her at all times. She's going to help by reading through our chat and telling me all of your answers. So she's an important person for us today. At the Children's Science Center, we do a lot of science, right? It's right in our name. So that's what we're going to do today virtually through this computer. And I'm going to need your help at times using that chat, telling me what you think we should do, or if you have any answers to some of my questions or problems. All right, give me thumbs up if you all are ready to go. All right, excellent, excellent. Well, the first thing I want to start with is something that you probably interact with every single day. I have some of it here in this water. I have some of it here in this water. It just looks, they look normal to me. Let's see if I can see water. They all look the same, right? Let's see, let's do a close up. Can we see our water swooshing and swirling here? But there's actually something really special about our water. It's made up of really tiny, tiny things we call molecules. Those molecules make up really everything around us. And water has two special ones in it. It has hydrogen and oxygen. Whew. Oxygen, we use that every day. Ready? Let's practice our oxygen use. Big breath in, then big breath out. Try again. All right, I've got a lot of oxygen in me now. Well, our oxygen is in our water and it also has that hydrogen. When we want to say water, but in chemical form, we call it H2O. We have H's, that's the hydrogen, and oxygen, that's the O. And if I want to be able to tell what's in my water, if there's anything different chemical or something was added, we can test out the amount of H's inside of it. So each of these beakers here full of water has both hydrogen and oxygen. Let us test out the amount of hydrogens in our water. How do you all think we can find hydrogen inside of our water? Use that chat feature. Tell me what you think. How can we test out and determine the number of hydrogen molecules inside this beaker of water? While you do that, I'm going to make sure I have all of my science equipment with me while you write in the chat. Let's see, I've got this over here. We'll use this.
So Rohan said a microscope.
Oh, a microscope. That's a great thought. Microscopes help us look at things that are super teeny tiny. Well, I don't have a microscope, but I do have a magnifying glass, and this lets us look at things that are really small. So let's try out my magnifying glass. Well, I definitely see the water, but I'm not seeing any individual H's and O's yet. So this might be good for looking at things that are a little bit bigger than molecules. All right, see what else do I have in here? Got my safety goggles. Get those ready. And I got some gloves. Let's get those ready too. What else do we think's in the chat? How can we count the H's and O's? This glove on and this. Maybe we take a look at what else is in my bucket here that can help us count our hydrogens. I've got a cup and I can scoop water with that.
So we have a couple different answers now. To weigh the water, pH strips, to boil the water, water test stick thingy, bunch of different great answers, guys.
I like that. So things we can boil the water, we can test it with different strips or different chemicals. I found scissors. I don't think these are going to be helpful. Let's see.
How about we do an experiment like someone in our chat said?
Let's do an experiment. That's excellent. And I think someone else said the things about pH, and that has the H in the word already. And I do have some of this chemical that says pH right on it. Let's see what this tells us. All right, this bottle says it is pH test indicator. Oh, so this can test something, and the word indicator, That means to indicate, to tell us something. So this can tell us the pH or the amount of H's that's in our water. So I think we should use this chemical and do a little experiment to test out. What do you all think? Thumbs up if you think that's a good idea. All right, lots of thumbs up. We've got our pH test indicator here, and although it's a large bottle, I think I have something to help us get it in smaller amounts. Aha, all the way at the bottom of my bucket, my special magic science wand. Okay, no, it's just a pipette, but this allows me to pick up liquids in small amounts and drop them in exactly where I want. And it helps me get the same amount each time. So I'm going to go ahead and take my pH indicator, use my pipette, and I'm going to give about 5 milliliters each into each of these beakers, and let's see what happens. If you see anything happen, tell me in the chat. All right, here we go. Let's go ahead and test this middle one first. All right, so we put our pH indicator in. Oh, something definitely happened. What do you all see? Something definitely changed with our experiments.
Yes, everyone in the chat seeing the color change. Everyone's seeing it turn green.
Our color changed to green. All right, so I know I have this water changes green. Let's see, let's do a hypothesis. That's when we take a scientific, educated guess. I know that I have water in each of these other beakers. So what do you think will happen when I put my pH test indicator into each of these beakers? Do you think the same thing will happen? Will it turn green like this indicator solution in our first beaker? Or do you think it will change a different color? And if so, what color? All right, there's your hypothesis to make. If I add pH indicator into my other beakers, what will happen? All right, while you are writing down some guesses, I'm going to go ahead and get started putting our pH indicator in each beaker here. All right, let's get the same amount as last time. Perfect. Here we go, our first test. Let's see if it was the same or different. Here we go. Whoa. I think just by using our visual observations, our hypothesis of something different would happen is correct. Let's see if the other beakers change the same color or if they change to different colors. Here we go. We've got one there. All right, we've got this one. Ooh, that one's a cool color. And all the way down at the end. All right, I'm going to give each one of these a nice swirl so that pH indicator can get all the way mixed in. And then we'll do some observations about each of these water beakers and the chemicals that might be inside of them. Okay, so this was our first one. It turned nice and green. Now, our second one we did, definitely not green, right? What color does this look like to you all? What color does this look like?
Everyone's saying red in the chat, and we got some orange, reds.
I'd say it's definitely close to red, maybe a little bit orange. What about this next one? What color does this look like? Are they the exact same or a little bit different?
Everyone's saying it's red.
Yeah, so it definitely is red, but my eyes, because I'm so close to it, can tell that this is a little bit orange. So this one I'd say is really red, and this one is just a little bit orange. Okay, let's look at the other side of our beakers and what happened to these? Definitely not red compared to our first beaker. Close in color, but this one looks a little bit darker. Ismail, what are we seeing in the chat?
Yeah, we see green color. One is clearer than the other. A little bit of dark green, a little bit of blue. All these great answers in the chat.
I like that we said one is even clearer than the other one. So we have our regular green, and then this one's kind of a darker teal little green. And then this one almost is close to blue. Still a little green, but there's some blue in this one. Now, another hypothesis, do we think that each of these beakers had the same thing inside of it? Or is there something different in each of these beakers? Based on the chemical experiment we did with our color change, what do you all think? Do they all have the same thing? Or do they have different chemicals inside of them?
Everyone in the chat thinks it's different amounts, different things in each beaker. Yep, everyone thinks it's different.
different. That's a great hypothesis. We do have different things in our beakers, and we can tell because of that color change. Our pH indicator uses color to tell us how many hydrogens in our water are in this beaker. Now, this middle one, this green, tells us that it's neutral. This neutral color means that there is just water in there. Our H2Os are all balanced, no extra H's or no extra oxygen. So we got our regular water here. Now, when I was doing and setting up for our experiment earlier, I had some chemicals out. However, I think they got kind of mixed up. So now I don't remember which one was in which beaker. But we do have a chart, something that can help us figure out which one is which. Bismaya, let's get our special chart for our pH indicator so that we can check. Thank you.
Go.
Here we go, our pH indicator chart. So the first one over here, what do we think? Does this fall towards the top of our pH scale or down here at the bottom? Let's look at our color.
Everyone's saying it's at the top.
Yes,
and they're right.
definitely up here at the top with our red and oranges. Now, when we have a color change with red and orange, that tells us that there are a lot of extra hydrogens in our water. And things that have lots of extra hydrogens are acidic. So this top of our scale are things that are very acidic, like soda and lemon. Oh, I remember I used lemon powder in one of these, and then I used citric acid. That acid is right in the name. So which one do we think of our really red solution and our kind of orange solution? Which one is which? Citric acid is kind of on the line of our kind of like our battery acid. Things are very acidic. And then our lemon is kind of just underneath. So let me know if you think the red is citric acid or lemon, or if you think the orange is citric acid or lemon. Let's see. So no, really red is going to be something very, very acidic. And it looks like lemon's kind of a little bit below it.
Everyone's saying citric acid is red. We have a couple of citric acid is orange. So we're kind of on the fence. Let's see. Everyone think about it really hard.
Our citric acid is going to be our red solution. This really dark red tells us that there's a lot of extra H's and it's really, really acidic. So that we'll give it a number 1 on our scale. Our orange is going to be more like a number 2, and that was our lemon powder because it's just a little bit less acidic than our citric acid. Our green, that first one we looked at, which tells us that it was neutral, it was just water. We can see right in the middle here around number 7 in the middle. This tells us our H's and O's are pretty equal. Now let's look at these two. Do we think our green and blues are more towards the top of our chart or the bottom of our chart? Let's look nice and close.
Everyone's saying at the bottom of the pH scale.
I agree with that. The bottom of our pH scale is where we have chemicals that have less hydrogen mixed in with that water. So less of our hydrogens gets us to the basic side of our scale. So remember, our oranges and reds were acidic, our green is neutral, and now our darker greens and blues tell us it's basic. We had my 2 chemicals today were borax and baking soda. Baking soda we use actually in a lot of kitchen chemistry where we cook with, whereas borax is something we actually put in our laundry to clean, and in one of my favorite experiments, slime. So which do we think? Do we think borax, which is right here on the scale, are kind of darker blue, darker green, and then our baking soda is a little bit lighter? Which one does it apply to? Is our light green baking soda or borax? This one was darker than our neutral, but a little bit lighter than the last one.
So we have some of our friends saying a baking soda is light green. Everyone's saying a baking soda is light green.
Yeah, I agree with that, which would mean by process of elimination and checking here on our chart, our last solution is what had the borax in it, which is really, really basic. So good. Now I remember which chemicals I put into which beakers. Whew. Now I can remember for the next time I do this experiment. Things that you can find around the kitchen or somewhere around you that are acidic are things again like sodas, and we said lemon juice. So any juices that you might drink, orange juice, lemon juice. I like to put limes in some of my smoothies. So even limes are kind of acidic. Now, and other things that are basic, it tells us things like seawater. Have you ever been to the ocean? that pH of it is a little bit lower on our scale. And so that gets us into the basic area. Now, while we've been doing this experiment, we've actually been doing a second one that we haven't even talked about yet. And this experiment has to do with the states of matter. Not states like the United States, but states of matter. If you know what I'm talking about, tell me at least one state of matter in the chat. All right, while we get ready for our next one, let's see, gotta adjust my goggles, make sure my gloves are still good.
So we have solid, we have liquid, we have gas. Everyone knows all these states of matter.
Excellent. Our three states of matter are solid, our liquid, and our gas. Now, which of those three did we use in our first experiment? Did we use a solid? Did we use a liquid? And did we use a gas? What did we use?
Our friends in the chat are saying liquid.
Definitely used a liquid, right? Now, before we even got to experiment, I added different powders into our water. That's what helped us see these different colors. So we got a liquid, that was the water, and our solid were the different chemicals that were added in. Now, did we use a gas at all or not so much? And seawater, I actually see a little remnant of solid stuck in this one from our borax powder, but did we use a gas?
Everyone in the chat saying no or question mark?
Yeah, question mark, confused. That's actually one of the best answers in science because that's when we get to learn new things. So question mark, did we use any gas in this experiment?
So our friend Rohan said if oxygen is a gas.
Yeah, oxygen is a gas. I'm using that gas to speak and breathe right now. We even did a little experiment about that earlier when we took a big breath, then went out. That oxygen goes in and carbon dioxide goes out. Well, to surprise you, we did use a gas in this experiment, just one we couldn't see. The air all around us is filling up all of the extra space in this container that's not filled up by liquid. So ready? I can capture all the gas. Now there's air stuck inside of this beaker. I wonder if there's a better way we can see this gas. Because right now it's just invisible to my eye, and I think it's invisible to you all too, right? Well, I have a special ingredient to add that will allow us to see the gas coming out of our liquids. So, my special ingredient. Here we go. I need it. Well, we're done with that. And I gotta get my special gloves. This ingredient is very dangerous. So I'm gonna make sure to use protective gloves when I handle it. Don't need that anymore. Oh, here it is. All right, I'm gonna be very careful with my extra material. It's in this bowl here. Do you all see anything in this bowl? What happens if I give a little bit of air to it?
Dry ice? Is it dry ice?
Yeah, great observation. This is dry ice. Now, dry ice is carbon dioxide, the stuff we breathe out of our mouth, taken and frozen into a solid. They make it super, super, super cold, so that way it can form into this solid. Well, when our dry ice comes in contact with regular air around it or with liquids, it heats up really, really fast. Does anyone know what happens when we heat water up? What happens when you maybe put a pot of water to cook mac and cheese on the stove? What happens to that water as it gets hot?
So in the chat, people are saying steam, it boils, it gets hot.
Yeah, it gets hot, it boils up, and then it turns into steam, right? So that water turns into steam. Well, water is a liquid and steam's a gas, so that makes sense. We call that evaporation, whereas a solid normally goes to a liquid and then to a gas, or melting, right? Well, dry ice skips the liquid stage altogether. It goes straight from a solid to a gas as soon as it starts to heat up. So as soon as I drop my dry ice cube into our liquid, we should see it change into gas. Oh, there we are. There's bubbles. You can see that gas bubbling up and filling up the rest of the container. Let's add a little piece to each one. Now, again, I have to be very careful when handling this because it is so cold, it could burn me. Normally, we think of burns as really hot, but this is so cold that it would burn even without heat. Here we go, adding in a little bit, add a little bit more. Dry ice is so fun to play with, but again, make sure I use my protective gloves. Now, wait a minute. Am I seeing this right? Did you come over and change the colors?
What?
That we didn't have yellow before. Can you all see how this green turned to yellow? And wait a minute. This one was dark green and now it's regular green. Well, I know that carbon dioxide is what makes up dry ice, and carbon dioxide is acidic. So when we think of that pH scale, it's actually going to rise all of our colors to the next color level when we add it in. So my red is going to get even redder. My green turns to yellow, and my greens, well, darker greens turned lighter because that acidic carbon dioxide is changing the chemical makeup of our liquid. So now as I add something more acidic to something basic, well, that one's even really, really yellow because I added a lot of carbon dioxide dry ice. It's going to raise that pH and we're going to become acidic now. I think this is pretty cool. I kind of want to try and take some of this gas home. So let's see. I don't need my big gloves anymore because I'm done touching the dry ice. But I want to capture this gas. Let's see. I have a cup. Let's see if I can pour some of my gas in. There we go. All right, so it's going into my cup. It disappeared. All right, let's try again. Pour that in, and I got it. Oh, there's a little bit in there. Can you see it? Okay, it went away. Oh, maybe this cup will work. Oh, this cup has a hole in it. That's definitely not going to work, but it makes kind of a little stream to come out. Can you all think of a way that we can catch gas?
So a couple of friends in our chat are telling us to use a balloon and inflate the balloon.
A balloon. I don't have a balloon, but I have some extra gloves. Let's see. I was going to check to make sure I didn't have any holes in my gloves, and I look good. So let's use this. Let's use this extra one. All right. Let's see. I've got my glove here. Let's see if I can capture gas just like a balloon. All right. Okay. So I got my glove here and we have our gas going. I've got some dry ice in this one. Oh, this one's got a lot of good bubbles in it too. Oh, there it goes. It's inflating the glove. So we can see that my gas is being captured inside of this. And I can feel the glove rising and getting really, really full. Oh, as soon as I let go though, our gas escapes. I've never been very good at tying balloons. So maybe there's another way that I can get it where I can capture it like the glove, but then I can hold on to it still. Okay. What else? What's another way that we can capture gas besides a balloon? All right, that glove's okay. We'll leave that one over there. Oh wow, look, this one's orange now. This one started out as green and is now very acidic like our lemon juice. Maya, what do you think? Do we have anything in the chat about how else we can capture gas?
A couple of our friends are asking if a Ziploc bag would work.
Oh, a Ziploc bag. I do have that. We can test it. Okay. All right, I've got my Ziploc bag. Oh, my Ziploc bag has holes on the side of it, though. It doesn't seem to want to fit all the way around my beaker, but it does have something to close it. So I definitely need something that I can close that air around. Oh, I know. I like to do this in the summertime. I like to go outside when it's really nice and warm, and I like to get a little wand and stick it in some solution and then go. What do you think that is? What do you think that is? I have a little wand, I put it in some type of solution and then go.
What is it, bubbles?
It is bubble. So let's see if we can try and capture this gas using bubbles. Now, I already have some warm water here because our warm water is going to allow our dry ice to go from a solid to a gas really fast. So let's put these out of the way. We can keep watching them while we do our next experiment and see if we can catch some of these bubbles. So got to get my gloves back on. Let's get this nice and open. We can get our hot air or hot water, and I can tell it's hot because there's some condensation inside of this tube where that water has started to evaporate, got really, really hot and turned into a gas. So I got my hot water. Gotta get my gloves back on. There we go. Ready. Okay, let's see. This is a big chunk of dry ice. I'm gonna put that right in the hot water. Whoa, look at all those bubbles already. So that hot water allowed us to get our solid to a gas very quickly. Now I need to capture this, so let's put our lid on. Okay, and we should see it start to come out of the tube instead of the sides of the container as I close it up. Whoa, now it just wants to get water. Can you see the liquid and the gas? Wow. All right, let's see. I've got my gas going. You can see it coming out of the end of the tube and out of the top here. Let's see, let's get a little bit extra of this. Oh, there we go. One of my favorite things in science is that we get to play around with all of the variables of an experiment. Variables are the things that we get to change. So like the amount of gas that's coming out or the amount of water that comes out too. All right, so we've got our gas coming out. Now let's see if we can catch it in some bubbles. I have some soap here, this blue soap I'm gonna try and capture my gas with. All right, let's see. Let's get some bubbles in there. Oh, I can see a couple forming inside of our soap. Let's see if I can turn my variable of my gas down a little bit because it's coming out so quickly. Let's see if we can change that. Oh, that looks like it's going a little bit slower. We get to do some really good experimenting today. All right, there we go. Let's try again, see if we can get our soap bubbles to catch. Oh, I see a little bit forming there in the soap. Whoa, did you see it? It came and popped very quickly. Let's try again. There we go, our soap bubbles. Oh, that one even got stuck in our soap. But as you see, once it pops, we can see the gas coming out. So we know that our gas is in fact being trapped by that soap. Let's see if we can get the biggest bubble possible. Here we go. Oh, I got a couple. Oh, I'm trying to catch it too. Nope, that one just popped. Oh, let's see if I can get this one. Oh, they keep popping. Does anyone know why I can't catch this bubble? Why can't I hold on and catch this bubble? Oh, I almost held that one.
In the chat, our friends are saying it's gas. It can't be held.
You're right. I can't hold this gas. As soon as I try and hold it, I can't do that. But what about the liquid part of the bubble? And would I be able to hold a liquid? Oh, just for a moment. Let's try again. Well, I know I can hold on to solids, but the liquid's a little bit more tricky. As soon as the liquid soap touches my glove, there is too much friction. The friction on my glove is what pops the bubble. That's the same thing as why you see when you blow bubbles. They float in the air, and then as soon as they touch the ground or touch something like you, your shoulder, your head, then it pops. So if I'm able to get my friction on my glove to come down, I might be able to catch a bubble. In order to do that, I need to find something that the soap likes, and soap happens to like other soap. So if I can get a little bit of soap onto my glove, then I might be able to catch it. So let's see, I've got my bubble. Let's get a little bit extra soap. There's a lot of soap on the excess of this. All right, got some soap. Let's see if I can get that bubble to stay in my hand. Oh, did you see it? For just a couple seconds, it stayed. So it's able to hold on to soap on my hand, but as soon as it finds just a little bit of friction, that's when it's able to pop. Ooh, I got it. Let's see if I can get two. Oh, that one's still there though. I can see how long I can hold it. All right, it's moving and jiggling and I can see that gas still inside. See if I can catch two. Oh, the bubble's even getting smaller as I can see little bits of the gas escaping on the sides of the bubble. All right, let's see if I can get any more. All right, let's see if I can catch that one. Oh, do you see the bubbles getting so much smaller? All right, finally, and pop. There was just a tiny, tiny bit left in our soap. Whew. Science gets a little bit messy sometimes, and that's one of my favorite things. We figured out how to catch our soap, well, how to catch our gas, right? And we had a little bit of that liquid on my hand that stayed. And we had a solid. So we have all three states of matter. But we want to learn a special word today. We know when dry ice goes from a solid to a gas super fast, we get this look, right? And we call that sublimation. Sublimation is when it just completely skips that liquid step. So instead of ice with just water, ice being a solid, going to a liquid and melting, and then going to steam, our dry ice, carbon dioxide, gets to just skip that step completely. It's breaking the science rules, which turns out to be pretty fun for our experiments. All right, let's go ahead and get cleaned up some. Okay, get my goggles ready. Oh, my gloves have gotten so messy. And get ready for our last experiment. I want you all to tell me though, while we're getting ready, what happened to the dry ice in our containers here? I wasn't touching it during this bubble experiment. So what happened to it? Where did it go? What do you think? Where did it go?
Our friends in the chat are telling us that it evaporated, it went away, it escaped, it stopped. A lot of evaporation in the chat.
Yeah, exactly. So it evaporated away. It left, and there's no more solid that is inside these beakers to allow it to change into a gas. So as soon as all of the solid is gone, no more gas for us to see. And I like that it changed into our different colors. Who can remind me, did these liquids turn into acids or bases? Got all that extra dry ice gas stuck in here. What do we think? Did they go to the acid or a base?
Some of our friends are telling us it went into acids and bases.
Oh yeah, so you're right. Some of them still stayed kind of basic, right? But we shifted along that scale up to the acidic side. All right, let's get all cleaned up because our next experiment, if you can believe, gets even messier than this. I would love to know what some of your favorite chemical experiments are. Go ahead and put in the chat your favorite thing to do with chemistry or with science in general.
Some of our friends like volcanoes.
Ooh, volcanoes are great. Those we can do with acids and bases, like our vinegar and an acid, and then our baking soda and base. Pour them together and poof, an explosion.
And we have some slime fans in the chat.
Oh yeah, slime is always fun. I'd love to know your favorite things to put inside slime.
Slime is a popular one. Everyone just likes any kind of slime, I guess.
Any kind of slime. I love using slime because it uses borax, right? We used that earlier, or sometimes use contact solution if you don't have borax to help our slime go.
So Allison's favorite experiment is elephant toothpaste.
Elephant toothpaste. Ooh, I know that one, and that is a huge, big explosion. That one's really cool to see. All right, let's make sure my goggles are all cleaned. What else? Any other fun experiments?
Some of our friends in the chat love milkshakes.
Ooh, milkshakes and food is a great thing to do with chemistry, right? We mix and match things, mix them all up until it creates something new. Our science today is not going to be kitchen science because we can't eat any of our materials here. But I bet you can find out some that you could do with adults to create something that you can make and then eat. All right, are we ready for our next experiment, our biggest and crazy experiment of the day? If you are, I want you to give me the biggest movement you possibly can on your screen. Go crazy. All right, I think that was some pretty crazy movements. Now, our third and last experiment, we're going to keep with our theme of using water, right? Our first experiment, we had water in our beakers with different chemicals added in. Our second, we used water and dry ice to capture the gas inside bubbles. And this one, we're going to use water to help dissolve some chemicals. Dissolve, that's a special and kind of funky word. You know what dissolve means? Go ahead and put it in the chat. We'll see how many of you know as we get into this experiment. So the first thing we are going to need is our hydrogen peroxide. Hydrogen peroxide is very similar to water. It's a clear liquid, but it has an extra oxygen. You remember talking about our water, we have H2O. We have hydrogens and oxygens. Well, our hydrogen peroxide has H2O2. So it has an extra oxygen hanging around. But that extra oxygen is kind of silly, kind of crazy, and it likes to leave. So if I were to leave my hydrogen peroxide out, then my extra oxygen will just float away and go into the air. But that happens very, very, very slowly. It would take us a long time to sit here and see it. So we have some other things that we can add to make it go faster. So I've got my protective gloves on. I've got my protective eyewear back on. Let me make sure it's nice and clean. There we go. And I think I'm ready for our hydrogen peroxide. Let's see if we can watch the oxygens leave and go into this big beaker. Here we go. It's in there. Do we see any oxygens leaving? And I see a couple little bubbles from when I poured it and some air got caught, but I can't watch those oxygens leave yet. I need to do something to be able to make that happen. Now, I have some water as well in this cup here, and I have a special solid that's going to allow our experiment to go faster. This is called potassium iodide. Potassium is in bananas, and iodine or iodide is in a lot of different chemicals. So when we've mixed these two together, we've created this solid crystal. If I take my solid crystal and I add it into my water, let's see, I want to get a full tablespoon, fill that all up. Looks kind of like salt almost, but a little bit bigger chunks than salt. I'm going to go ahead and add this in here. And now I need to make it dissolve. Do we have anyone who knows what the word dissolve means?
Yeah, a lot of our friends in the chat are telling us that it means to disintegrate or to break into pieces. A lot of answers like that.
Exactly. So it means to kind of break apart and make go away. So as I dissolve my crystals, I am mixing them so well into the water, into this liquid, that I can no longer see them. They're still there. It's just mixed so well with the water, we can't see them anymore. So I'm going to mix this up and make sure that all of my potassium iodide crystals are gone. All right, here we go. I'm seeing less and less with each stir. Some other things that we can dissolve are lemon powder, if you want to make lemonade, or I like to put sugar in my tea. I'll mix that in and make that dissolve. Here we go. Okay, I don't think I have any more crystals left. It is just our water. But my water is a little bit different color now. It's slightly yellow because that iodide in our potassium iodide crystal has a slight yellowish color to it. So now I can tell that everything's mixed in, all dissolved, and that little bit of a color change lets me know that it's ready. So we got our hydrogen peroxide. We're just waiting to watch those oxygens leave. And we have our solution here. Our solution we are going to call a catalyst. A catalyst is something in chemistry that makes things go a lot faster. So if I just wanted to walk around the Science Center, just walking at my normal pace, and then someone came and brought me a catalyst, I would be running really fast. And that's what our chemical is going to do for that oxygen. But even though it makes it go faster, we still have to find a way to see it. So does anyone have a suggestion from maybe something we did earlier to see how we can look at a gas? What could we do?
So some of our friends are telling us to use food coloring or maybe bubbles.
Oh, we have maybe some food coloring or bubbles. How about both? We have bubbles, right? This is what we can use the soap to catch that gas in. And then we also have some food coloring to make it look cool. We can add different colors. So I'm going to add some soap in first. Here we go. Soap, lots of soap for lots of bubbles. And then we need to add in some food coloring. So let's see. My favorite color happens to be green. So I'm going to add some green in. All right, let's get some going down the sides here. And then Miss Maya, I think you told me earlier, you really like yellow, right?
Yeah, I love yellow.
All right, let's do some yellow as well. And then let's have our friends vote on the last color. We have either red or blue. What color should we do, red or blue?
So we have a couple red, a couple blue. I think we have a little bit more blue.
Okay.
Blue. Yeah, I'm seeing more blue than red. I'm sorry, red, blue one.
All right, let's go with some blue. So we have our different colors in here so we can see our experiment go. All right, here we go, some colors there. And now we need to add our last part. that catalyst to make this go a lot faster. So right now we have our big, large container here with just our hydrogen peroxide, some soap to hopefully catch the bubbles, and our food coloring. Let's go ahead now and add in that catalyst. I want you all to count down with me. Ready? In 3, 2, 1, go. All right, there our catalyst is added. Oh, I see some movement. There's lots of bubbles. Here it goes. Oh, excellent. Our beaker is overflowing with bubbles. And can you even see there's steam coming off of it right now? Whew, it's still going. So when we added that catalyst, our potassium iodide mixed into that water, it made all of the oxygens in that hydrogen peroxide want to leave very fast. But it's because of that soap that we're actually able to see it. The soap is what captures all of that gas and allows all of these huge bubbles. And then the cool colors right there is what helps us see it too. Now, one of our friends said that their favorite experiment was elephant toothpaste, and that's what we just got to see. We call it elephant toothpaste because all of these stripes here kind of make it look like toothpaste, and the only thing big enough to use this for toothpaste must be an elephant. Now, the last thing I want to talk about with this experiment was we saw some gas coming up off the top of it. And when I put my hands right here, it was really, really warm. So I have something for us to test out how warm something is without having to use like a thermometer like we would use. It's at the bottom of my bucket. Here we go. I have this temperature gun and it uses infrared light to measure temperature. So right now, the measurement inside of my beaker, whoa, is 123 degrees Fahrenheit. Whew, that's hot. Let's see what the bubbles on the outside are. Ooh, our bubbles on the outside are cooling down. They're only at about 89 degrees Fahrenheit. That's about the temperature it is outside today. So we've got our cooling bubbles. Let's see, is it still hot in there? Oh, still 119. So this is very, very hot. I'm going to make sure not to touch it so that I don't hurt my hand. But I'm curious now to know the temperature difference between our hot elephant toothpaste and our dry ice. Does anyone want to take a guess as to how cold our dry ice is going to be? Let me put my gloves back on so I can pick some dry ice up. And I want you to tell me, how cold do you think our dry ice is? Now, for reference, our heat right here was about 120 degrees Fahrenheit.
So we have some answers saying in the negatives, super cold, -57, -1 kajillion thousand.
So I guess it's definitely negative numbers below 0. Well, water freezes at about 32 degrees Fahrenheit. And although this isn't water, this is carbon dioxide, it's pretty similar. So let's see, our frozen dry ice here is -46 degrees Fahrenheit. So that's a temperature from about 120, this is about 110 right now. It's cooling down to -40. Whew. It's almost 150 degree difference between this hot elephant toothpaste and this cold dry ice. All right, I want to thank everyone so much for joining us today with our Children's Science Center and our different activities with our pH, our boo bubbles is what we call them, with our dry ice and soap, and our elephant toothpaste. Thank you all so much, and I hope you have a great rest of your day.